Let us begin the EE555 discussion on Wednesday, January 29th, 2014.
Thanks a lot. Good morning, everybody. We had a small delay. We are looking for a pen, actually, that's why. All right, so let's get started. Today we'll see 3 problems on queuing theory as well. And I'm going to post the problems in the second part. I'm going to give you a paper that has 4 problems, but we'll see 2 of them today and the rest next time. All right? So let's begin with this one. There are 2 servers A and B in the system. A server A is available to provide service for a time that is exponentially distributed of 2 hours. The server is not available for a period of time that is also exponential with mean 30 minutes. B works independently from server A but with similar work pattern. The time server B is available for service are exponentially distributed random variables with means 90 minutes and 40 minutes. Define an appropriate state of this continuous time Markov chain and sketch a labeled state transition. On the long run, find the proportion of time that neither server is available to provide service. What proportion of time be available for service? Okay, so we have a lot of questions. Understand the problem first of all? Do you want to see it again? So we have 2 servers, A and B. They are active and inactive for exponential. And we want to draw a continuous time Markov chain. And this might look like your homework too, where we have mixed states, okay, in any case. So that it's kind of different than style of systems that we have. Okay, so let's, first of all, what is given over here? Let's start with the mu's and the lambdas. This is this the 29th today? I'll call this problem 0, okay? Alright, so it's given in the problem here that we have service time for the first server, which is a mean value of 2 hours, exponential with mean value 2 hours. As you see, it's in hours. So I'm going to convert everything to hours, okay? It's going to make the simpler anyway. All right, so 1 over mu A is 2 hours per customer. What else we know? It's 1 over mu B is 3 over 2 hours per customer, 90 minutes. And also, the inact is also exponentially distributed with parameter 1 over 3. Similar bits available. 2 over 3 is 40 minutes, 30 minutes, okay? Also, 1 over mu A prime, let's call it this way, is equal to 1 over 2. Hold on, yeah. One over mu B prime equals to 2 over customer. No, it's not per customer, I'm sorry guys. It's, just waiting time. Alright, so the continuous time Markov chain, for what is the state, or what a state can be in this case? Something that makes sense. Any ideas? Let's start, for example, define the state as, first of all, we have to differentiate if one server is busy and the other is not. You know, what is the state? We have 4 combinations, and that basically, right? So let X be the state of the system where X equal if no server is available. We can, if A is available, we can call it B if B is available, and here we can call it 2 if both are available. All right? Okay, so with that said, now we can go Markov chain, the continuous time Markov chain. I'm going to do it to the next page. To have it in one single page is more easy. Okay, so we have state 0, state A, B. We can draw state 2 here and state B here. Now, do you agree so far? What is the rate we go from 0 to A? 0 to A means we have an arrival that goes, right? So this happens with exponential with parameter 2 for A. What about the rate we go from 0 to B is 3 over 2. Sorry, it's 3 over 2. I'm right. 3 over 2. From A to 0, 1/2. Don't mix those two things. One is 2, the other is, right? Okay. This is the service time. This is the time it's inactive. This is B to A is, sorry, where we are, to B, 3 over 2. B to A is, am I talking about B to A or A to 0? A to 0. We were talking about this, right? So this is 1 over 2. What about the rate that we go from 2? If you understand these 2 to A and 2B, that's it. 2 to A, what does this mean? B is finished service, right? Okay, perfect. So what is the rate? 2 over 3, right? Okay. Three over. Okay. Similarly, we have from 2 to B is 1 over 2, and B to 2 is 2. Do you have any other case? You have 2 over, we need another here that goes back from B to 0, and this rate is how much? 2 over 3, that's right. All right, so that's all. If basically the most complicated part, how to go from one state like this to the other, you have to think that the other guy finished. Okay. So now we can take all the cuts of the graph and find the balance equations, right? Do you all agree? Okay. So now what is the rate we go out of the state? It's 2p0 and 0, right? 2p0 plus 3 over 2p0 equals the rate we go 2 over 3pb plus 1 over 2pa. Do you all agree? Same for this cut. Cut the graph into 2 halves, okay? Just make a complete cut and take the rates. Because you might find these, I don't know, somehow weird looking, and you have to cut it in the right way. In this case, it's PA times 1 over 2 plus 3 over 2 PA equals the rate with 2/3 P2 plus, from here is 2P0. All right, so we need another equation, one more, and then the trivial. I'm going to put 2/3 P2 plus half P2 equals 3/2 plus 2 PB. And then we need that P0 plus PA plus PB equals 1. There is no point taking another balance equation here because it's going to be an equation to solve the system, right? All right. What else? If you solve the system now, we won't do it now. Something like that. P0, 4/65, PA equals 65, PB, 9/65, and P2 equals 36/65. Factors we sum to 1, so we are good, all right? So the question is, in the long run, find the proportion of time that neither service is available to provide service. Does this mean? P0, right? So the proportion of time neither server is available is P0 equals 4/65. All right, so what proportion of time would serve available for service? Okay, so if we add only PB, we need to add.
I'm sorry. When you say the proportion of time neither server is available, is it because the server is it probably the blocking probability which is asked for here?
Exactly. I mean, it's not really. It's the time, right? We have a problem that says for how much they serve and how much. We don't talk about arrivals, right? It's a continuous time Markov chain where we talk about service times, active times. So it's different than the regular queuing systems we have seen, right? So we want to find calculate basically stationary probabilities in a continuous time Markov chain. That's a problem about. Make sense? Right? So time would server B be available? Proportion of time server B is available equals PB plus P2, because in this B is available, right? We know that. So it's going to be 45/65. Make sense? Okay. If we all agree, we can continue. Okay, so next problem is from here and is as follows. Customers arrive at a shop according to a Poisson process of rate hour. The shop has 2 clerks to attend to the customers. Suppose that it takes a clerk an exponentially distributed amount of 5 minutes to service 1 customer. What is the probability that an arriving customer served? And then find the mean number of customers in the system and the mean time spent in the system, and find the probability on 4 customers in the system. All right, so we have a system. We have a system here. What kind of system is this? It's MM2, right? We have Poisson arrivals, we have 2 clerks, 2 servers, and exponentially distributed service times with mean 5 minutes. All right, perfect. So I think we almost everything from the theory, we can apply what we know, right? So problem number 1. What do we know? We know that lambda equals to 12 customers per hour. And I'm going to convert this in minutes. Why is that? Because minutes over here, we have hours above. Let's make it all equal, right? Equal, same unit. So this is 5 customers per minute. 12 over 60, right? Per minute. Okay, so we have 2 servers, and what is this rate? 1 over mu equals 5. This means that 1 over 5 customers per minute. Okay, so this is, as we said, is an MM2. And what is the rho of this MM2 system? Lambda. And this is equal to 1 over 2. All right? So the probability customer has to wait, which is the first question, is equal to what? You will see this notation all the time with represented as probability of W being greater than 0, right? The waiting time. And what is, how is this stated in terms of the number of customers in the system? Greater or equal than 2, right? Why is that? Because we have 2 servers, they are both busy. If n is greater or equal than 2, then we have to wait. This is equal to that. Do we know that? Seems we know that, right? Yeah. Because we have servers are busy, then you have to wait. No. You arrive in the system and there are 2 servers and there are 2 customers in the system being served, right?
So, but when you're talking about the system, aren't you talking about the number of served as well as the one in the queue? So if you just have 2 in the queue, those will be served by the 2 servers. So shouldn't it be?
No. Do you agree with what he says? You go to an office, there are 2 servers and there are 2 people being served. Do you have to wait? The same thing here. We don't count, right? You just go and how many customers in the system you have. All right, so do the generic formula where 2 is the size of the C, basically, in our case, right, or M, whatever you represent it. This formula here is what? You saw that in for the professor. We know that this is equal, actually, this is to the power of M over here, I think. M factorial 1 minus P. And this is equal to R square, rho square, to 1 minus rho P0. Do you agree with that? That's in the lecture notes. Also, this is equal to PM over 1. We'll use that too. PM, where M is this, over 1 minus rho. Do you agree? I think you should make a formula, as you know, guys. I told you last time too. It's going to be really helpful for you. All right. P0 is what? It's this long, ugly formula that we have. 1 plus M rho M factorial 1 plus summation from n equals 1 to m minus 1 times, m rho into the power of n over n factorial. And this is the power of minus 1. And here we just substitute. This is equal to 1 plus 4 rho square 2 plus 2 rho over 1 to the power of minus 1, and gives what is that? It's basically 1 plus 1 over 1 plus 1, which means that PW great, if we go back here, it's this guy here is 1/3, and if we substitute also those, they give 1, so it's 1 over 3. Okay. I'm sorry. All right, so let's go to the section. It's question B. Find the mean number of customers in the system and the mean time spent in the system. Again, you have seen these formulas in the lecture notes, so it's just an application of that. So expected number of n is what? In the generic case, it's m times rho, rho s, 1 minus rho, where s to what? Probability that we have to wait, right? N greater or equal to, and this is 1 over 3 from the previous A. Okay? Calculate the expected number of customers in the system as 2 plus 1 over 2, 1 over 3 over 1 over 2 is equal to 4/3. Customers, that's the unit. Okay? And average time in the system, spent in the system. This is the total time, right? Expected T. Anybody? Slow for that, right? Great. So this will be the number of customers divided by lambda, right? And this is 1 over 5 times, and this is 20 over 3 minutes. Nothing really strange so far, right? Okay, so in the question we need to find the probability that there are more than 4 customers in the system, okay? 4 customers in the system, and we have, what do we have? We have 2 servers, 4 customers in the system. Have you seen this probability again? Have you seen any formula for that? There are many ways to calculate it if you want. One is to say 1 minus n less or equal to 4, right? And sum all these probabilities. Because it's discrete, we have 0, 4, if you want to do it this way. Otherwise, there is a formula for that. First of all, generic representation is summation from 5 to infinity of, and this can be shown that it's P5 1 minus rho. Okay? If you see the formulas for you can see the recursion over there, how you can express. We usually represent this in terms of P0, but you can represent probability, or the first probability of the summation, like starting from this and going above. This is equal to n greater or equal to 5, and you can represent that from the starting point, like the above. All right, so, but we know that Pn equal to lambda to the power of n, m factorial, m n mu to the power of n times P0, and this is for n greater than m. So P0, we have find P0. Where is P0? P0 is here, is 1 over 3. So we'll use that. Thus P5 is equal to power of 5, 2 factorial, 2 to the power of 3, mu to the power of 5, P0. And this gives, if you just do the substitution, It's 48. From A. So is that P greater than 4 is equal to P5 over 1. This is equal 1 over 48, 1 minus 1 over 2, and this is 1 over 24. And that's just another application of MM2, right? You see here. Any questions? So now we'll continue to another a bit harder problem. And also we'll see for your project, mini project. Have you seen the mini project? Do you think you can do it? What do you think, guys? It's not hard, it's just that some people might, you know, not be familiar with Excel. I hope not many. Alright, so let's go to problem number 4. So inquiries arrive at an information center according to a Poisson process of inquiries per second. It takes a server half a second on average to. The service time is exponentially distributed. How many servers are needed if we require that the mean total inquiries should not exceed 4 seconds and 90% of all queries should wait less than 8? Similar to a homework problem, right? You have something. And the second question is, what is the resulting probability that all servers are? Do you understand what's asking? How many servers are needed? We need to design some applications, the constraints. And we need to find how many servers we need for this to satisfy the requirements. It's a nice engineering problem. And the same can happen in a computer network. Let's say links do you need, or how many servers do you need, or how, you can map it to something real. All right, so this our lambda, first of all, is 10 per second. Per second, and 1 over mu in our case is 5 second over per. All right, that's the two things we know, and the first question is that we want to satisfy those two constraints. We want expected t be less or equal than 4, right? 4 seconds, and at the same time satisfy the other constraint, which is p waiting time. 90% of all queries should wait less than 8 seconds. So how we translate that in terms of W? Probability of W, it should be what? 8. 90% of the customers. So this probability should be what? Greater than 0.9, right? All right. If you draw the diagram, you basically take this, the 90% of my traffic should satisfy that. So what else? Let's try now to translate expected number of t probability to things that we know, such that we can calculate M system. So X is given by what? Expected W plus expected S. Just the definition, right? And this should be less or equal to 4. Which means that, how much is the expected service time? This is half, right? So expected expected W must be, this is equal to 0.5, 3.5. But can we calculate expected W? we can, what? The number of customers in the queue. And then we can use the formula that we know. Is that expected W, which is equal to NQ over lambda from little to rho over 1 minus rho. And here we have the Erlang-C formula, right? How do you represent it with 3 parameters or with 2? It's common to use both. Some books use the one. In any case, I'll use 3 now. The difference is that lambda over mu, the ratio, or you give both. That's the question here. So the number of servers is given, and I'm going to give both parameters, lambda and mu. Same thing. Actually, here we give more information. It's more than and here we need to divide by lambda. So EW is equal to C M2 over M mu 1 minus rho, which gives C M10,2 greater or equal to 3.5, right? And this less or equal to 3.5 times mu times 1 minus rho. I just did 2 steps. Is clear? And then this gives that CM2 is less than 7. We can put M inside, M minus M, lambda over mi times mu, which is equal to 7 lambda 5, 1 over 5, right? Mu minus, sorry, 5. Do you agree? 1 over mu is 2. Half. Mu is 2. So the ratio is 5. Alright, so, and this needs to be not equal, greater than 0, right? Have a distribution here. How much is that? We need to take, first of all, the minimum, right? What do we need to do? Let's start, let's say, from what's the minimum value we can say we can take for this being non-negative and non-zero? So let's start with mu equals 6 and see what we get. So m equals 6, we have rho equals lambda over mu. This is 5 over 6. And in this case, expected t will be expected w plus 1 over mu, and this is mu m, 1 minus rho, c sigma 2 plus 1 over mu. Okay? And this is equal to 1 over 2, 6, 1 minus 5, 6. And along C we get that this is 0.5875, and this the final answer is 0.7931, which is less or equal to 4. That so the first constraint is satisfied for the minimum number of servers we allow. Do you agree, guys? So we need to check that because we have 2 constraints. Are you lost? Okay. Let's try the second constraint, as we said, which is P. Let me write also PW less or equal to 8, greater or equal to 0.9. And which means PW less or equal to 8, it should be, I'm going to here, we don't know this result yet, but we will prove why this is the case. See below, because I don't want you to spend 1 hour trying to understand why this formula is here, while the proof is below that. Okay, so this is 1 minus the number of servers, 6,10,2, e to the power of minus 2, 1 minus 5 over 6, in a while. And this is equal to 0.99, which is greater than. So the second constraint is satisfied as well. Okay. The question is now, okay, let's prove that. This proof is also in the Leon Garcia book. If you have this book, the chapter for queuing theory, it's same as the professor basically. You know, the material that you have seen in class is there too. So you'll see more material, but this proof is there. All right, so let's go ahead and prove this result, and we are good to go. Any questions? Okay, so let's go. First of all, I missed that other question, which is probability that all servers are busy. P also is equal to Pn greater or equal to M, and this is 610,2, and this is given. This is 558. 1. So that's the probability here, and now let's prove the result. The CDF of W, where W is for an MMC system, is FWX is equal to 1 minus C from the number of servers, lambda mu, and the other factor is minus M mu 1 minus rho X. We want to prove this result. That's the asterisk. Okay, so this is kind of, nobody expects you to be able to, it's a, kind of involved result. So let's see how we can derive this answer. The waiting time distribution for MMC, that's what, we know what it is. To analyze, to map this to what can happen in the system in order for us to wait. Okay, we have waiting. So let's consider the conditional probability. Conditional T that there are J minus M in the queue. Customers in the queue given that all servers are busy. NT is greater or equal to M. Okay, that's when we wait really. So let's consider this case. So what happens? The probability NT equals J, given that NT is greater or equal to M, is the total number of servers. We take this conditional probability, okay? This is just, we just take the intercept, meaning just apply what we know. We have Pnt equals Nt greater or equal to m, and in the denominator is Pnt to m. Okay? What do we know from that? We know that j is greater or equal to m, so this translates, this is equal to Pnt equals j over Pnt is greater or equal to m. Means j is greater or equal to m, right? And this is equal to, we have seen this formula here, rho j minus m pm. Formula is, what is the denominator? We used that previously, is rho m over 1 minus rho. And this gives the pm cancels here from here, so it's 1 minus rho m. Okay? So I'm marking this equation as 1. And what can we see from here? This is the distribution geometric, right? So the conclusion here is that when the MC system is busy, it performs like an MM1, because the same formula applies for MM1 exponent here, right? We have m equals 0 in the other case, but if we start from m and above, it's an MM1, right? So this is a geometric. I need to skip a lot of wording here. I'm going to add up later. We don't have the time to finish this. So this is a geometric, and then I'm going to add it later, okay, for a better explanation. And then let's go ahead and see what happens when we have a customer waiting, arriving in the queue. K customers in the queue when somebody arrives. So this guy must wait for K plus 1, right, service times before this customer enters the system. Do you agree with that? So we have to sum basically K plus 1 exponentials. That's all. So the waiting time for our customer, if there are K plus 1 customers in the system, summation of K plus 1 are exponential random variables with parameter mu m times mu, given by an Erlang m K plus 1 distribution, right? Erlang PDF.
Excuse me? It's about 9:20, so whenever you're done.
All right, thanks. This is f x comma lambda comma k lambda to the power of k x k minus e minus lx k minus 1 factorial x comma lambda greater or equal to 0. All right? Lambda equals mu times m and k equals 1. Let's write in our problem. We have, and what is the rate? The total rate is, we have all the servers busy, m times mu. Those exponentials. All right, guys? So this is, W in this case is equal mu x to the power of k, k factorial, mu, I'm gonna stop here. Okay, I'm next time, or I'm gonna post the rest of the, okay? I'm sorry for that. We spend time more on the other things. All right, thank you guys.
EE555 discussion on Wednesday, January 29th, 2014.